Hello everyone, my name is Mujtaba Nafez and today I'm excited to present our work Adversarially Robust Anomaly Detection and Localization which is accepted at CVPR 2025. Let's begin with concept of anomaly detection. It is typically framed as a binary classification problem between normal and anomaly sample. However, during training, the model is only exposed to normal data. The goal is to learn the distribution of normal samples so that at test time, the model can effectively determine whether a given input sample, is normal or an anomaly. In addition to detection, when a sample is identified as anomalies, the model should also produce a localization map that highlights the specific region where the anomaly occurs. As shown in the figure above, the image on the left is a normal industrial cable. In the center, we have an abnormal sample, and on the right, the localized defected area of the abnormal sample. In adversarial setting, a small, often imperceptible perturbation are added to the input. This perturbation can cause the model to misclassify even clearly normal or anomalies input. For instance, in this figure, by adding subtle noise to the image of a pandas, the model incorrectly classify it as a given. A common defense strategy against such attack is adversarial training, where the training data is augmented with adversarial examples. The model is then trained on both clean and perturbed input to improve its robustness. In this paper, we examine the adversarial robustness of anomaly detection and localization networks. Based on our experiment, we find out that most state-of-the-art models in this area are still highly vulnerable to adversarial attacks. For instance, as shown in the figure, methods such as general AD, GLAD, and recontrast perform nearly perfect under normal condition. They accurately localize the anomaly region, which is highlighted in red. However, after applying an adversarial perturbation, these models completely fail. They classified normal regions as anomalies and anomalies regions as normal. According to our experiment, even the most common defense strategy, adversarial training, does not work effectively in this context. Why is that? Because during training, these models have access to only normal data. They never see real anomalies, and therefore they cannot be trained on adversarial version of anomalies sample. As a result, the model does not learn to defend against attacks targeting anomalies input and making them highly vulnerable. But how can we address these challenges? Ideally, to build a truly adversarially robust anomaly detection system, we would need access to real anomalies data during training. And to make the localization component robust as well, we would also need the ground truth localization map of those anomalies. However, in practice, both are rarely available, which makes this problem particularly difficult. So, in PatchGuard, we introduce a method called foreground-aware pseudo-anomaly generation. We start by using GradCam to identify the foreground region of the input image. However, since GradCam can be noisy or imprecise, we enhance it by applying light augmentation to the image and then computing GradCam on each version. By taking the intersection of those GradCam outputs, we obtain a more reliable estimation of the foreground. Next, we randomly select a rotated rectangular region within this foreground area and apply a set of hard augmentation uh, to simulate a defect on the input sample. This allows us to create pseudo anomaly samples that appear realistic and are grounded in the image context. Our pseudo anomalies have several key advantages. They remain close to distribution of inlier data, which, according to prior literature, helps in better modeling the decision boundary. And also, since we generate these anomalies ourselves, we also have access to their exact localization map, which enable us to supervise to training supervisedly and robust anomaly localizer. So uh, we also use a VIT based architecture, vision transformer based architecture, to effectively leverage the generated pseudo anomaly data. In VIT model, each image is divided into patches, and the model produces a feature representation for each patch. We utilize this property by introducing an attention-based discriminator that classify each patch as either normal or anomalies based on its representation. Since we have access to localization map uh, for each patch, for each pseudo anomaly sample, we also know the ground truth label for each patch. Uh, Whether it is normal or anomaly, we have this information. This allows us to compute a patch level cross entropy loss across the entire image and use it to update the network. Within this setup, we can now train our model adversarially. We include both normal and pseudo anomalies input, aligned with their adversarial counterparts. To generate this adversarial example, we perturb the input image but by maximizing the sum of patch level cross entropy losses, which make the model more robust to attacks which targeting both normal and abnormal regions. Uh, in PatchGuard, we made an important observation related to transformer attention mechanism. Let me first introduce the concept of attention degree. The attention degree of a transformer attention head refers to the average number of input embedding each output embedding attend to. According to our experiment, a higher attention degree improves adversarial robustness. We also provide theoretical justification to support this claim. In the bar chart, we split the Bratz dataset into five groups based on their attention degree as measured by our model. As shown in both the right and the left bar chart, splits with higher attention degree are significantly less vulnerable to adversarial attacks. You can also compare the clean trained models on the left with adversarially trained model on the right. You will notice that the range of attention degree is generally higher in adversarially trained model. Motivated by this, motivated by this observation, we introduced a regularization loss term that encouraged the model to increase its attention degree. As shown in the formula, this regularization term works by minimizing the overall loss, which implicitly increase the attention coefficients in the denominator, thereby promoting a higher attention degree. So now PatchGuard incorporate this attention degree regularization term into its loss function and is trained in an adversarial manner. This combination helped the model become more robust by both resisting adversarial attacks. As you can see, our model outperforms existing state-of-the-art model in anomaly detection by a significant margin. On average, PatchGuard achieve higher accuracy and robustness, clearly demonstrating the effectiveness of our approach. This performance gap become even more pronounced in anomaly localization, as you can see in the table. We present PatchGuard, an adversarially robust anomaly detector and localizer that use a novel foreground-aware pseudo-anomaly generation and an attention degree regularization term supported by theory and experiment. PatchGuard also outperform as a state-of-the-art model in both detection and localization under adversarial attacks. Thank you all for your time and attention. If you have any question, please feel free to reach out via email.